imperfections into solids, so solid it will be dividing into two categories, amorphous material, or you can say atoms in an amorphous solids are arranged randomly, so there is no repeated order of your atoms. In case of crystalline materials, atoms in a crystalline solid are arranged in a repetitive three-dimensional pattern, long range order. So in case of crystalline materials, all the atoms it will be perfectly arranged, or you can say into the repeated order. In case of amorphous material, it will be randomly occupying the space into the structure. So all the metals are crystalline solids. Many ceramics are crystalline solids. Some polymers are crystalline solids. See some of the examples. In the crystalline solid, it will be the perfect order structure. In the case of non-crystalline, or you can say the amorphous material, it will be having a random order structure. So some more terminology: polymorphism and allotropy of the metals. The ability of the material to have more than one structure is called polymorphism. So basically, it is a behavior of the metal to show the different crystal structures at the certain temperatures or within a temperature range. It means what? At different temperature, material having a different structure, and structure is directly related to the properties of the material. So different temperature having a different property of the materials. The atomic arrangement may be changed according to the change in temperature. Such a change in a crystal structure is called as a polymorphic changes. Assume that the perfect order structure for materials, but into real materials it will be the crystalline defects or lattice irregularities. So that irregularities present into the structure by the atoms, it will be called as a imperfect structure of the materials. So that imperfect structure, it will be said to be imperfections into solids. So most of the real materials have one or more errors in perfections, with dimensions on an order of an atomic diameter to the many lattice sides. So just you can see, any deviations from the perfect atomic arrangement in a crystal is said to contains imperfections or defects. So there are major four categories of the crystalline defects. First, zero-dimensional defects, or you can say the point defects occurring in a single lattice point. One-dimensional defect, linear defects, or you can also say the dislocations occurring along a row of atoms. Two-dimensional defects, or you can say the planar defect or surface defects occurring over a two-dimensional surface in the crystal. Three-dimensional defects, or you can say the volume defects, bulk, void defects. So defects influences the electrical and the mechanical properties of the solid. By adding alloying element to a metal is one way to introducing a crystal defects. So crystal imperfection have a strong influences upon many properties of the crystals, such as strength, electrical conductivity, and hysteresis losses of the ferromagnetisms of the materials. Thus, some important properties of the crystals are controlled by as much as by imperfections and by the nature of the host crystals. Crystal defects and its classifications. So based on to the point defects, or you can say the zero-dimensional defects, vacancy kind of point defects, Schottky kind of point defects, self-interstitial kind of point defects, Frankel kind of point defects. In case of line defects, or you can say also a dislocation kind of defects, so edge dislocations, screw dislocations, surface defects, grain boundaries defect, tilt boundary defects, twin boundary defects, stocking fault kind of defects, volume defects, inclusions, voids. A solid solution. Solid solution means one metal A, that will be dissolved into the B. So one metal that will be dissolved into the another metals, and it forms the new materials. Suppose the added atoms that will be from the materials, it will be called as a solute metal atoms. So solute metal atoms, it will be occupying the space into the solvent structure of the materials and to form the new materials, and that new materials, it will be said to be a solid solution. So as per the definitions, a solid solution is a solid state solution of one or more solutes into a solvent. Such a mixture is considered as a solution rather than a compound when the crystal structure of the solvent remains unchanged by the addition of the solutes, and when mixture remains in a single homogeneous phase. So single homogeneous phase means it will be mix a single solid materials. So let us see some of the examples. The first figure indicating the perfect structure. So you can considering it will be the solvent structure. If there is some alloying element will be added into the structure, so it will be changing a new structure. So new arrangement you can find. So that new arrangement from the previous one, that will be representing as a imperfections into structures. If it will be having the same size of atoms as we discussed for the solute and solvent, so that will be called as a substitutional kind of solid solutions. If it will be the size is different for the solute and solvent, so that will becoming a interstitial kind of solid solutions. If the solute member having a smaller size, so that will be representing into the third figure small solute atoms. If the solute atoms, it will be having a larger size, so you can see that large solute atoms. So if it will be having a smaller size of the solute, it will be making a interstitial solid solution. If it will be having a same size, so that will be making a substitutional kind of solid solutions. Most important theory into the imperfections into solids, and that will be your nuclei and the growth of a nuclei. So in the case of solidification process, result of casting of the molten materials, it will be having two steps: nuclei formation and the nuclei grow to form the crystals and grain structure. You can see the initial positioning, all the metal alloys that will be having a higher temperature into the liquid state. Then you can carry out the solidification process. So temperature drop down, and some of the temperature like the higher melting point of the metals, it will be considering as a starting point of the solidification in the case of binary alloy. So at initial state, the nuclei formation, nuclei is nothing but the solid tiny particles of either metal A or either metal B, or you can say one of the metal, it will be having a solid tiny particles, and it will be representing by the nuclei. After certain time of solidification process, that nuclei having a growth, and finally it will be converting into grain structures. So crystals grow until they meet each other. So finally one nuclei will be meet with the neighborhood nuclei, and that neighborhood nuclei will be meet with their own neighborhood nuclei, and it will be making a grain structure. So one grain size, it will be differ from the another grains, and that will be separated by the grain boundaries. So finally you can get the structures in the form of grains and grain boundary. So start with a molten material, all are liquids. Polycrystalline material, just you can see the structures. So grain boundaries, the region between the crystals, transition from lattice of the one region to that of the others, slightly disorders, low density into grain boundaries. So low density, it will be for the high mobility of the atoms, high diffusivity and high chemical reactivity. So here just you can see the one grain size, it will be differ from the another grain size with respect to the number of atoms it will be present, its direction, its basic structures, and occupying the space into the grains. So each and every grains, it will be having a different angles. So it will be representing over here small angle grain boundaries, high angle grain boundaries, angle of the misalignments. So some of the defects it will be present into the grains and grains boundaries. So that will be the representation of the polycrystalline materials. So finally into the solidification process, your liquid of your binary solid solution materials, it will be having a final structure in the form of grains and grain boundaries. So start with the defects, or you can say the imperfections, the point defects. The point defects are where an atom is missing or is in an regular space into the lattice structure. Suppose in the perfect order structure, one of the atoms it will be permanently leaving their own positioning from the structures and it will be generating the vacancy. So vacancies, this is especially true at high temperatures when atoms are frequently and randomly change their positions. Leaving behind atoms lattice sites is called a vacancy. Or you can see by different authors, vacancies are empty space where an atom should be but is missing. The higher is a temperature, more often atoms are jumping from one equilibrium position to another, and large number of vacancy can be found into the crystals. So interstitials, or you can say the atoms that are squeezed in between regular lattice sites. If the interstitial atoms is of the same species as a lattice atoms, is called as a self-interstitial. So here you are discussing with the vacancy kind of point defect. From the figure you can see that one atoms it will be missing their own positions from the structures and it will be out of the structure. So by leaving their positions it will be generating the vacancy. So such kind of defects it will be present into the materials. It will be called as a vacancy kind of point defects present into the structures. Second one, self-interstitial. So one extra atoms it will be positioning in between perfect order structures. So as from the figure shows that one extra atoms it will be occupying the space into the perfect order structure and it will be also making a defects, or you can say the imperfections into perfect order structure. So that will be representing as imperfections into solids, and by the addition of the one extra atoms it will be called as a self-interstitial kind of point defects. So in case of vacancy, atoms are leaving their own positions, and in case of self-interstitial, one extra atoms it will be added into the structure. So by leaving their positions and by additions, it always make the imperfections into structures, and that imperfection it will be said to be a imperfection, or you can say the defects. Schottky defects is a type of vacancy in which an atom being free from regular site migrates through a successive steps and eventually settles at the crystal surface. A pair of anion and cation vacancies, as shown into the figure, one positive ion and one negative ion, so it will be leaving their own positions and it will be occupying the new positions at your boundary region. So always it will be in the pair of positive and negative ions from the structures. So that will be called as a Schottky kind of imperfections or defects. A Frankel defects is a pair of cation, or you can say the positive ions vacancy, and a cation interstitial, or it may be also be an negative ions vacancy or anion interstitial, or you can say that the combination of vacancy and interstitial is called a Frankel defect. So three definitions for Frankel defects. Let's see with some of the examples. Here is the perfect structure of NaNCl. So now you can see one positive and one negative, it will be leaving their own position from the structures and it will be occupying the new positions in between structures. So by the leaving their own positions, it will be generating the vacancy kind of point defects, and by occupying the new space into the structure, so that will be the interstitial kind of point defects. So you can see that it will be the combination of vacancy and interstitial kind of point defects, and that will be your Frankel defects. Line defects, or you can say the dislocations. In linear defects, group of the atoms are in a irregular positions Linear defects are commonly called as a dislocations. Any deviation from the perfect periodic arrangement of the atoms along a line is called the line imperfections. So the line imperfection, acting as a boundary between the slipped and unslipped regions, lies in the slip plane, is called dislocations. These dislocations are generated and moved when a stress is applied. The strength and the ductility of the metals are controlled by the dislocations. So there are extremely two types of dislocations: edge dislocations and screw dislocations. Let's see with the edge dislocations. From the figure, the above portion it will be having a perfect structure, and below portion it will be having a perfect structure. So one extra line of the atoms, it will be into the structure, it will be addition of the one extra line of the atoms, and so it will be dividing into two parts: slip region, so above portion, and below portion, or you can say slip region and unslip regions. So after applying the stress, or you can see the shear stresses, that line of the atoms it will be moving into the structure. Let's see with the another figures. Here it will be the one extra line of the atoms A that will be added into the structure, and it will be having a line kind of dislocations. So above portion from the slip lines, it will be a slip region and unslip regions. So after applying the shear stress from the both the end on your slip and unslip regions, that extra line of the atoms A, it will be try to jumping over a B and try to jumping over a C, and finally you can see that it will be one of the edge of the structures. That's why it will be called as a edge kind of dislocations. You can see that if the one extra line of the atoms it will be added into the top positions, that will be considered as the positive edge dislocations. If it will be found at the bottom of the structure, so it will be called as a negative edge dislocations. Screw dislocations. So just you can apply, if the edge dislocation it will be present into the structures, and you can apply the torsional effect. So it will be moving in like into the figures. So basically Burgers vector, that will be the distance it will be measured from one atom to another atoms if the line dislocations it will be the present. So in case of edge dislocation, it will be the perpendicular to the dislocation line. In case of screw dislocations, it will be the parallel to the dislocations line. If the both are present, or you can say your component, it will be subject to the torsional as well as your shear stress, so it will be having a mixed kind of dislocations. Planar defects into the solids. Suppose the top surface of your structure it will be get damaged at certain angle, so that boundary it will be twin boundary kind of defects you can see into the structures. The essentially a reflection of the atoms positions across the twinning plane. Stocking foil kind of defect. For a perfect structure it will be having a ABC kind of sequence, but if you find ABC and BC, so there is a certain rearrangement of the layers of your ABC, and it will be called as a stocking foil kind of defects. Most important theory: difference between the edge dislocations and screw dislocations by the definitions. In the case of edge dislocation, a form of a line defect in a crystal lattice in which the defects occurs either due to the presence of an extra plane of atoms or due to the loss of a half of the plane of the atoms in the middle of the lattice. As from the definition, the screw dislocation, a form of a line defects in which the defects occurs when the planes of the atoms in the crystal lattice trace a helical path, or you can say torsional stresses, or you can say spherical load path around the dislocations line. Outcome of Graham standing in case of edge dislocation: when we apply stress on a crystal having a edge dislocation, the dislocation area moves parallel to the direction of stresses. In case of screw dislocations, When we apply the stress on a crystal having these defects, the dislocation's area moves perpendicular to the direction of the stresses. Stresses in case of edge dislocation, stress is comparatively less complex. In case of screw dislocation, stress is comparatively complex.